Okay, welcome everyone to the penultimate talk in our quantum summer series, hosted by the Harvard-Radcliffe Society of Physics students. The quantum summer series is a segment of our Chilloquium speaker series. My name is Andrew Vinitsky. I'm an undergraduate studying physics and mathematics at Harvard, and I'm one of the organizers of Chilloquium. I'm here today with my co-moderator, Minchell Park, and we're very honored to have Professor Schleier-Smith from Stanford speak with us today. As always, if you have questions at any time, you can raise your hand at the Zoom participant sidebar and we'll call on you, or you can probably send a message to me and I'll ask for you. We encourage you to raise your hands to ask questions yourself in person in order to make this feel as conversational as we can. So we'll generally be prioritizing questions asked in person over privately messaged questions. In the spirit of keeping this a more relaxed and personal conversation, we also request that everyone be muted unless they're speaking and also have their video on if you're willing and able. Lastly, for those of us who are joining us for the first time today, and if this is the first time you've received one of our emails, make sure to sign up to our Chilloquium mailing list on the link I just posted in the chat. We just send a reminder email on the day of the event, as well as a weekly Chilloquium email the week before, so you know what talks are coming up. So if you want to stay up to date on our talk schedule, fill out that quick 15-second form. All right, so with that, let's get started. Minchell?
So with that, let's get started. Professor Monika Schleier-Smith is a professor at Stanford University. Professor Schleier-Smith received bachelor degree at Harvard College with concentration on chemistry and physics and with secondary field in mathematics. Professor Schleier-Smith's lab aims to advance our control and understanding of many particle quantum systems by engineering new quantum states and Hamiltonians with ensembles of laser-cooled atoms. Professor Schleier-Smith, please.
Well, thank you for the invitation to be here virtually. I titled my talk today, Atoms and Photons, from Fundamental Physics to Quantum Technology, although actually the order of the talk is sort of the reverse. I'll start with some kind of motivation from the area of quantum technology and kind of move towards some explorations in fundamental physics. And along the way, I will stop and say a little bit as requested about kind of my career trajectory. And I really would encourage you, but I think this is, a fairly small group, so I definitely encourage you to, raise your hands and ask questions and, steer this to whatever is of most interest to you. But I thought I would start by sharing a little bit about kind of what I find fascinating about quantum mechanics. And in particular, we'll start with something that you might kind of read about if you read the news at all, which is that these days there are a few different platforms of kind of engineered quantum systems in the laboratory that are kind of reaching the threshold of quantum advantage or quantum supremacy, where one has systems of individual quantum bits that are well enough controlled to operate in a regime where the behavior of the system can't be calculated classically, even on the world's largest supercomputer. And it suffices to have something like 55 well-controlled particles to access this regime. And so, so why is that? It seems sort of surprising that such a small system can't be simulated even on a classical computer. And the reason has to do with the difference between sort of classical and quantum information, right? So on your classical computer, information is encoded in bits that, are maybe a 0 or 1, or you could represent those by some magnetic domain on your hard drive that's pointing this way or that way. In your quantum computer, information is stored in, well, qubits. What does that mean? My picture for a qubit is as something that's basically like a little magnetic moment that could point up or down, but could also point in any direction in between. And the way we interpret this is that if it's pointing up, that's the one state. If it's pointing down, it's the zero state. But generically, if you try to measure the state of a qubit, there will be some randomness in the outcome. If it's sort of pointing halfway in between, half the time you might get 0, half the time you might get 1 if you do the same experiment many times. So reading the state of a quantum bit is a little bit like performing a coin toss, but it isn't just any coin toss. It's a very special type of a coin toss. And I actually recently had kind of the assistance of a professional animator in explaining what's so special about a quantum coin toss. So we're gonna do sort of a very quick video clip of me trying to explain what's so special about quantum coins. Bear with me. The simplest quantum system is a quantum bit. which, like a classical bit, can be in the 0 state or the 1 state. The remarkable thing about a quantum bit is that it doesn't need to be in just the 0 state or the 1 state. It can be in what's called a superposition of the two. Fundamentally, it's unknown and unknowable whether the qubit is in the 0 state or the 1 state until a measurement is performed. And when the measurement is performed, it's almost like it has to decide. So I like to use kind of the analogy of a coin, right? A coin is a system with 2 states, heads and tails. And the superposition is a little bit like a coin that's floating in midair and it hasn't decided whether it's going to land heads or tail. So now the really neat thing, though, is that in a quantum system, you can have a phenomenon that's equivalent to me tossing a coin and you tossing a coin, and we repeat this experiment 100 times. And every time I get heads, you get heads. And every time I get tails, you get tails. But if I look at my tosses alone, the outcome always looks flat random. So there's this randomness, but there are correlations in the randomness. And that tells us that there's some information that I don't have. My coin toss looks random. You don't have it. But when we compare notes, there's actually some information there and not just randomness. So this idea of having information that's encoded in correlations, this is known as entanglement. And this is really the key resource for quantum technologies. Okay, so this phenomenon of entanglement, this idea that there can be information that's not here nor there, but sort of encoded in correlations between different particles, is in some sense what is absolutely what gives rise to this complexity of quantum systems. Because it means that even if I have just 2 qubits, I need to keep track of, let's say, correlations between these 4 different measurement outcomes. If I get one heads, is the other one more likely to be heads? If I have, 3 qubits, I need to keep track of all of the probabilities and correlations between these 8 measurement outcomes and so forth. And for every qubit I add, the sort of number of different possible outcomes of the system that I need to keep track of and keep track of all the correlations between them grows exponentially. And that's why sort of this description of even 50-some qubits won't fit on a classical computer. So that then actually is sort of has a number of implications, ranging from the fact that once we have a system of many particles that behave quantum mechanically, maybe that's electrons in a molecule, it becomes difficult to calculate things like molecular structure or chemical reactivity that depend on that. But it also is the reason why we think that if we can control quantum bits or individual quantum degrees of freedom well enough, then perhaps we can build computers that have some power to solve problems that classical computers can't. And sort of the last aspect of this that is worth pointing out is this sort of complexity, the necessity of kind of controlling all these possible correlations is in some sense at the heart of the difficulty of building kind of engineered quantum systems, something like a quantum computer that can actually have this impact that we dream of. Nevertheless, there are kind of increasingly sort of a few platforms out there where it's become possible to have a high degree of control over quantum systems in the lab. To control these correlations and entanglement among even not just 2, but let's say tens of particles. And one of the kind of leading platforms, which is one that is near and dear to my heart, is the platform of laser-cooled atoms. And in particular, I've shown here a couple of pictures from a few different labs, and you'll notice I have a number of pictures from Harvard, where some of the most beautiful experiments are currently being done, showing individually trapped atoms. So one has here sort of order 100 atoms, which can be individually controlled. Each one is trapped at the focus of a laser beam. And this is sort of a remarkable system in the combination of kind of control and also scalability. And so these systems of laser-cooled atoms have a number of different applications. One is actually, for example, the best clocks are made of these laser-cooled atoms. The second, as you may know, is defined in terms of an oscillation frequency in the cesium atom. So if you can do very good spectroscopy on atoms, you can use that to build a very good clock. I mentioned from the outset, there's the direction of using these atoms as individual quantum bits in the effort to build a quantum computer. But somewhat nearer term, even before sort of having some universal quantum computer that can do any calculation you might dream of, what is a nearer term application that's explored in a number of different research groups around the world is asking, can one build sort of special purpose simulators where one has a well-controlled system that can explore a class of problems that are hard to solve classically. Like, for example, can I use atoms trapped in some lattice configuration to simulate the properties of a certain class of magnetic materials? If I have sufficient control over the atoms and their geometry and the interactions between them. And so that's a direction that's explored in these systems. And one of the key things that I mentioned, right, that's important for this is not just being able to sort of position and take pictures of the atoms, but also to be able to control their interactions. That's necessary to be able to generate these correlations, this entanglement. It's necessary if you'd like to, let's say, mimic the magnetic interactions in a material. And in fact, that's also something where there's a quite powerful toolbox. So there are a number of different systems where one has highly controlled interactions between these laser-cooled atoms. That might be that the atoms are optically trapped in a standing wave of light, and if they sit in the same well of the lattice in which they're trapped, there'll be some collisional interaction between them. Or one can engineer longer range interactions by taking ground state atoms and exciting them to Rydberg states where the electron is highly polarizable, and then they can interact over even longer distances, long compared to sort of the spacing on which they can be trapped and manipulated. But one sort of common feature of these interactions is that they, as you might expect, decay with distance. That's true of generally forces in nature decay with distance. So interactions tend to be local. Things talk to other things that are near them. And that can give rise, in some pictures I've shown here, to situations where, for example, these individual, earlier I talked about qubits, but we can also think of spins that point up or down. They organize themselves, let's say, in some kind of checkerboard fashion through the influence of these local interactions. So here's a couple of pictures showing that in different physical systems. What I would like to kind of, and okay, there's a question. Andrew.
Yeah, so before we go more into the, I just want to step back to the sort of applications of quantum computing with these sorts of platforms, and especially like the Rydberg atoms that you mentioned. Like at Harvard, for example, there's a lot of experiments done, like at the Misha Lukin's lab, for example. There's the recent result where he had some very large number of qubits made with these, I think it was a Rydberg array.
Yes, yeah.
And then on the other hand, there are like you mentioned, there are a number of other approaches, right? There's trapped ions, and then there's a like last week, Professor Deborah spoke with us about the idea of the superconducting circuit and how you can couple it to this Josephson junction and make this really good or pretty stable qubit. Can you speak a little bit about the thrust of each of these experimental directions? And because it seems like a lot of people in like the people at Google and IBM are pursuing superconducting circuits. A lot of research is involved in trapped ions and Rydberg arrays and that sort of thing. And they're all sort of working towards a similar goal, but they kind of appear to be at different stages and moving at different velocities. Can you talk a little bit about that?
Yeah, so I think one of the kind of general questions that, so there are a number of different sort of figures of merit that you might think about in asking sort of, how close am I to a quantum computer? So there are things like, what is the fidelity of the gates that I can realize, or the fidelity of the entanglement that I can realize? Then there are questions of kind of scalability. How many individually controlled qubits can I have? And also kind of things like flexibility of control. What are the ways in which they can talk to each other, and the sort of can I only have nearest neighbor interactions? Can I have more control over the structure of gates? And so all of these platforms have somewhat different kind of benefits and drawbacks. I would say one of the key things about the neutral atoms, you also said they're moving at different paces. One of the things that I find really exciting about these neutral atom platforms is, first of all, just the pace of development. Just a few years ago, kind of the highest gate fidelity was about 80% or something, and now it's at 99 point something, 99.7 maybe, or so. So this is like very rapidly improving, and the scalability. So for example, the superconducting qubits, somehow at the end of the day, you are kind of fabricating these devices, and you need to work on making them, as identical as possible. Atoms, every atom, an atom isn't, every rubidium atom is the same as every other rubidium atom, and there's this sort of really remarkable progress in being able to kind of controllably position these in large two-dimensional arrays. So kind of on the metric of scalability, these systems are really nice. And then kind of one other aspect that is kind of worth mentioning about the atomic platforms is, you asked about computation, but kind of going beyond that, I mentioned there are these other applications, for example, in clocks, the fact that kind of the fundamental properties of the atom are very well defined, allow also these other kind of applications in precision measurement. But I'm not sure, does that answer the question? There are so many metrics one could compare. I think maybe just to add to that, all of these I would say are worth pursuing, right? Because they have their different sort of features and challenges. But in terms of the trajectory, I would say these neutral atoms are very exciting at this point.
Yeah, absolutely. Yeah, thank you so much. That makes a lot of sense.
Mm-hmm. Yeah, thanks for the question. Great. Yeah, and so indeed, these images I've shown here are precisely from Michel Lucan's lab at Harvard, showing this array of, what is this? I don't know, in this case, probably about 100 Rydberg atoms that have formed some kind of checkerboard pattern because of these strong interactions between neighbors. Or in this case, have formed actually a highly entangled state where every other atom is up, but you don't know whether it's the even ones or the odd ones, and it's an equal superposition of both. So yeah, okay, so these are kind of some of the nice things that are possible with these kind of local interactions between the atoms. On the other hand, there are reasons why you would like to go beyond the situation where atoms only interact with their neighbors. And so one kind of, I would say, limitation of these sort of most naturally occurring interactions has to do with the connectivity being restricted to being local. So just to sort of say why that matters, we can take a classical example of, the internet. Isn't it wonderful that I'm here in Palo Alto and you all are presumably in Cambridge, and yet there's no barrier to us just exchanging information for practical purposes instantaneously, right? Thanks to the internet. This sort of connectivity is really important for allowing sort of governing the flow of information. I actually, particularly over the pandemic, spent more time talking to some group of physicists distributed around the world than to my next door neighbor. And so somehow non-local connectivity can make a huge difference in the classical world, but also in quantum systems, sort of the connectivity provided by interactions matters for what you can do with a given system. So just to give a couple of examples, if I have a collection of spins or qubits on a lattice with nearest neighbor interactions, that is actually a natural geometry for making a quantum state known as a cluster state that is a resource for computation. But if I had the same form of interaction and every atom talked to every other one, it turns out that that form of interaction naturally gives rise to a state known as a squeezed state that is a resource for enhanced precision measurements, like improving those atomic clocks. If you have every atom talking to every other atom, but there's a certain kind of randomness in the interactions, that can give rise to a situation where some information that's initially encoded locally in one of these atoms is very quickly kind of delocalized and becomes kind of scrambled and hidden in complex correlations and entanglement among these many particles. That type of model, that's actually used as a model for what might happen to information that falls into a black hole that's rapidly scrambled and appears to be lost. And if you have sufficient programmability of the interactions between individual quantum bits, then you may be able to take some real-world optimization problem and actually map it to the problem of minimizing the energy of a particular interacting quantum system you can realize in the lab. And so that can be a kind of computational paradigm. So broadly, the structure of interactions governs the form of entanglement. And so it would be useful to have a system where one can sort of have versatile control over the graph of interactions. And so I thought I would kind of give one example from these various examples I gave above. I'll zoom in on one, which is sort of how would controlling the interactions allow you to perhaps solve some optimization problems, just as a concrete example. And so I like this example because it's another one where if you kind of surf the internet and ask, what are quantum computing companies doing, you'll find various examples where they tell you that they're going to do things like solve your scheduling and logistics problems, help you optimize fleet operations for holiday deliveries, optimize the returns on your financial portfolio. So what are they doing? In some sense, so first of all, there are lots of questions actually about to what extent quantum systems can help with these types of problems. So lots of fundamental scientific questions, and what role entanglement might play. I always wondered, though, when I read these things, like, how do you take a real world problem and map it onto some physical system that you have in the lab? So I was really happy when I learned about kind of, a concrete example of this. So the concrete example is, we're at the beginning of the academic year, and one of the things we need to do is schedule classes. And so if you take a very simple example of a scheduling problem, it would be something like, imagine I just have 2 time slots in which I can schedule classes. There's the morning slot and there's the afternoon slot. And I have a bunch of students with classes that they want to take. And I want to schedule them so that if a lot of people want to take, class A and class B, those are in different time slots. So one way you could kind of encode this problem or represent this problem is draw a graph. And each vertex is a class. And each edge is weighted by the number of people who want to take like both of these two classes. And so if I want to kind of schedule this well, what I should do is if a lot of people want to take both classes, I should put them in different time slots, right? So the 2 colors will be morning and afternoon. In other words, I should sort of cut the graph into 2 groups in a way that I cut the heavily weighted edges. So I'm going to separate this into sort of like the red nodes and the blue nodes, which will go in the morning and the afternoon time slots. And if I'm as physicist, though, the way I can think about this is I can think of red and blue as just 2 states of a qubit or a spin, right? Spin up and spin down. And essentially what I've done here is I've said if I have a heavy bond, that means those spins want to anti-align. Right? They want to point in opposite directions. Those classes will go in different time slots. So I can map this real world problem onto minimizing the energy of a system of interacting spins. So this case where the spins want to anti-align, if there's a heavy bond, that's called an anti-ferromagnetic interaction. They want to anti-align. So that's kind of neat. I took this real world problem and I mapped it to this minimizing the energy in an interacting quantum system. And if I want to be able to do that, the sort of tools you need some way of encoding a spin, let's say in the internal states of an atom. We need interactions, which generically here, right, for some arbitrary graph that encodes my problem should be non-local, not just interactions on a lattice. And I want some programmability of the interactions. Okay. So this gets me to kind of what do we do in our lab. So one of the things we've been working on in my lab is having control over non-local interactions between distant atoms, which are generated by using light to sort of convey information from one atom to another, right? So similar to the way that we're talking over the internet at practically instantaneously, a photon can travel practically instantaneously from one atom to another. And now the idea is that we'd like to sort of have every atom be able to talk to every other, and in addition have some way of using light to control which atoms talk to which other atoms. So that's kind of what we're aiming for, and just sort of, before getting into programming the interactions, I'll just give you a general flavor of sort of more concretely, how can I use a photon to convey information from one atom to another? So, let's say I have my 2 spin states or 2 internal states of an atom. What I would like to do is have some process where an atom can flip its spin and emit a photon, and another atom absorbs that photon and flips its spin. Conceptually, that's the way we'll use photons to generate long-range interactions. And one thing you might worry about is, I don't want the photon to fly off in some random direction. I really want to be pretty sure that a photon emitted by one atom is absorbed by another one. And so for that reason, we put mirrors around the system. And now you get constructive interference that enhances the probability that an emitted photon will interact again with another atom instead of flying off out of the system. And so this general concept of sort of using what's called an optical resonator or an optical cavity to generate interactions between atoms is something that is already kind of quite well explored. And one of the places where actually, I first got into this was in the context of actually using photons to generate entanglement in kind of large clouds of atoms that constitute, in sort of a large system of many atoms, constituting actually an atomic clock. And in particular, by having sort of every atom talk to every other, by scattering photons amongst each other, you can generate correlations that basically sort of conspire to reduce quantum fluctuations in a measurement of, for example, how many atoms are up versus how many atoms are down. And so I've kind of illustrated that schematically here in some pictures showing the orientation of the total spin of this system of atoms and some squeezing in the uncertainty in that orientation. So here are a couple of recent experiments that use this kind of type of a system of atoms talking to each other with the aid of light to enhance the precision of atomic clocks. And this is sort of a line of research that I actually started in my PhD. That's continuing to be sort of pushed upon and applied towards increasingly state-of-the-art clocks today. This gives me an opportunity to sort of pause and say a little bit about kind of, this was sort of my starting point into this field of cold atoms and entangling atoms with light. And so I just thought I would kind of share, since I was asked to say a bit about my career trajectory, a picture of myself in 2011, sort of at the end of my PhD. This is the lab where we did a first sort of proof of principle enhancement of an atomic clock using these methods. And I thought I'd say a little bit about kind of my path from sort of being about your age, for those of you who are Harvard undergrads. So this is me right before and right at the end of my undergraduate studies. I'm in the courtyard of Winthrop House here. This is kind of me last year, at Stanford with my research group. So sort of what were the steps getting from here to there? So actually, sort of prior to arriving at Harvard, I had already been very fortunate to sort of do some summer research where I was really getting to read cutting-edge scientific literature and think about some ideas in the area of nanotechnology at a local company called MITRE, where I grew up in Northern Virginia. And so this had already kind of shown me that I had an interest in chemistry and in physics. And by the time I got to Harvard, I decided, I also always loved math. So I was a chemistry and physics major with a secondary concentration in math. And I realized that sort of the intersection of these interests in chemistry and physics and math was really quantum mechanics, right? There's sort of beautiful mathematics that describes everything from what's going on inside atoms and molecules that describes that, but where there's really sort of the fundamental understanding comes from really physics, right? And so that was something where I would say actually what motivated me a lot to kind of get into physics was this love of quantum mechanics. I had the fortune of doing undergraduate research, particularly with John Doyle, who some of you might know, who I also really kind of inspired me to go into this field of atomic physics as something where you really get to kind of, I see somebody applauding, good, yeah, where you really get to kind of play with quantum mechanics in the lab. I then, sort of knowing that kind of experiments with cold atoms would be a nice way to kind of pursue my interests in quantum, and particularly a nice way to get to sort of really do some hands-on, work in the lab, building things, building electronics and playing with lasers, but at the same time sort of having an elegant mathematical description that you can write down on paper and compare with the data. Those were things that really drew me deeper into this field of cold atoms. I did my PhD then at MIT, working with Vladimir Vuletich on this using atom-photon interactions to enhance an atomic clock. And then at some point towards the end of my PhD, I realized everything I had been doing was sort of what I might call quantum engineering. Like, we sort of could write down what we thought should happen in the experiment, and we knew if we did the experiment well enough that we should get a particular quantum state out that would be useful for a certain purpose. But I was also fascinated by this idea of going into a direction where you might build a simple model in the lab, but because of the complexity of quantum mechanics, you don't know what will happen. So what I would call quantum simulation. You build perhaps some model system that might capture the essential physics of electrons in a material, but you can't calculate it because of the reasons I gave before, but perhaps you can just build it in the lab and learn something. And so that inspired me to go do a postdoc in a group in Munich that is one of the leading groups working with optical lattices, so basically using standing waves of light to create some crystalline structure that could mimic the crystalline structure of a material, and trapping atoms inside that could mimic the electrons, and using that to explore sort of models of condensed matter physics with cold atoms. So I worked at the LMU Munich and Max Planck Institute of Quantum Optics, and this also, I would say, gave me exposure to kind of also different, ways of different scientific communities on different continents. And so this is kind of the geographical map of my career trajectory. Boston, Germany, and now California. I'm going to pause and ask whether there are sort of career-related questions before I say more about what are we doing now in my lab. Yeah, Andrew.
Yeah, this is just out of curiosity, and I was interested in hearing that you work in John Doyle's lab, well, maybe it's a selfish question because I also work in John Doyle's lab right now.
Yeah.
But which experiment were you working on when you were an undergrad here?
Yeah, so I actually, so it's interesting. So the summer of my freshman year, I sort of, scanned through what all the different faculty were doing in the physics department and saw something about atomic, molecular, and optical physics and thought that sounded fascinating and emailed John Doyle. But I also, I wanted to go home for the summer. And it turned out at the time, there was an experiment that John Doyle was leading that was at NIST, the National Institute for Standards and Technology in Gaithersburg, and that was not far from home for me, which was actually an experiment to measure the lifetime of the neutron. So the neutron, when it's not in an atom, actually has a finite lifetime of about 15 minutes. And there was a small research reactor there, a nuclear reactor that was a source for neutrons that were being trapped, and that lifetime was being measured, and I was doing a little side project on that experiment. So that was summer number one. Summer number two, I wanted to actually stay at Harvard and worked directly in John Doyle's lab, again on kind of a side project of my own, it was a very technical thing. It was basically building, if you imagine you have a laser beam that needs to get from one room to the other, and you want to make sure its pointing is stabilized. So it was actually building kind of the feedback control electronics and some piezo-controlled mirror to feed back to stabilize the pointing of a laser beam. And it was actually a really good project. That one didn't have a scientific outcome. It was very technical. But I kind of learned, a lot of really great experimental skills that I took with me into my PhD in experimental physics, and also just got a sense that, yes, I actually enjoy really working in a lab and doing these hands-on things and having to design some hardware. And then, so somehow I kept thinking about where I want to be. So the third summer, I thought, I would like to kind of go abroad for a change. I have family in Germany, and I asked John whether he knew of any opportunity to go to Germany, and he said, oh yeah, I have collaborators in Berlin. And like a day later, it was arranged that I would go spend a summer at the Fritz Haber Institute in Berlin, which is a center for doing some molecular physics. And there were experiments there having to do with actually decelerating beams of molecules, so that you can kind of slow them down and ultimately trap them and bring them to low temperatures and do some of the same kinds of physics that we're doing with atoms, but with molecules. And so that was, I actually ended up mostly actually doing kind of calculations related to the experiments there. And one of my big regrets is that I was too shy to go just ask people what all the equipment was in the lab. So for all of you, if you ever, experimentalists love showing you their labs. So that's kind of now I would never go to an exciting lab and not ask about all the equipment. But anyway, so that was more sort of theoretical work related to this molecular physics. And so those were kind of my 3 summers in between the years at Harvard.
I see. Yeah, very cool. Yeah. Did you ever consider going to Japan? Or I don't know if John was collaborating with people in Japan at that time, but
I don't remember whether that happened later or was happening already then. I have visited Japan and and enjoyed it, but I did not consider working there. I think partly there is something about getting to go somewhere that's different, but where the language, that was really nice for me about going to Germany. So and as you see, I spent a summer there, and then I did my postdoc there as well. And I actually feel very fortunate now to sort of be connected. So geography does matter. I showed this plot about sort of all that matters is connectivity in the internet, but really geography does matter. And I felt that also after doing a postdoc in Germany, I kind of was more in touch with certain research developments that had been going on in Europe than I probably would have been if I had stayed in the US. So
I see. That's really interesting. Thank you.
I see another hand up.
Oh, hi. I have a question. I have a question about as you have both experience in having a research in Europe and in America, I just want to ask about whether there's some difference in research style between the America and especially for Germany.
Yeah.
In terms of the topics or some kind of academia style or yeah.
Yeah, so I think one of the things I worried about when I decided to go to Germany was that it might be very hierarchical. So on paper, it kind of looks very hierarchical. So, here I would say there are different size research groups, but overall, kind of the sizes of research groups tend to be smaller, whereas I was working for, so my postdoc advisor, Emmanuel Bloch, was a professor and also a director at a Max Planck Institute, and had something like maybe, 6 to 8 different sort of experiments, each of which had some more sort of senior scientist also under him helping run the experiment. And then, so I kind of worried that it would feel very hierarchical. And what I found was that actually, even though on paper it looks that way, it was very flat, and sort of in the scientific discussions, everybody's ideas counted. And yes, I did in fact get to interact with my postdoc advisor, even though it looked like there might be this, level of separation between us. And he was very in touch with all of the, actually really details of what we were doing in the lab to an amazing degree. And so I came away thinking that some of the differences are really probably more dependent on the particular group and the style of the group than on the geography. Now, there are some differences in like resources. For example, at a Max Planck Institute in Germany, you're more likely to have some engineers who help with like the mechanical design or the electronics design and so forth, some kind of engineering staff. And then I think at sort of a later career stage, there are differences in sort of what it means to get a faculty position. So for me, one thing that I think was nice about coming back to the US is it's sort of very straightforward to get a tenure track faculty position where you're pretty young, but you're given, empty space and money and the freedom to do whatever you want. And in Europe, it's often more that you sort of at the same age would be still like under a more senior person, and it's sort of a subgroup of a larger group. And so that's kind of, maybe a little bit down the line for all of you, but I think there is that career stage where you're kind of wanting to start to be independent, where that might be a little bit easier in the US.
So in the research topic wise, it's kind of more dependent on the groups rather than the geography, you would say?
I would say it's more dependent on the groups, although there certainly are just, if some idea comes up in one place, that place might be ahead in that line of research. That can happen, but I think it's really more about the specific groups. So, yeah.
Oh, thank you.
Andrew.
Yeah, I just have another quick question. I was wondering so you mentioned something, or you mentioned like theory-related projects that you worked on. So have you had the sort of internal conversation about whether to do like theory, like physics theory, or like AMO theory versus AMO experiment, or like a combination of both, and how do you sort of navigate that decision process?
It's a great question. So I actually distinctly remember being an undergraduate, and in one of my classes, my E&M professor, who was Professor Tinkham, said he sort of like made some comment about his research or something, and said, everybody comes into college thinking they want to be a theorist, but you really should think about doing experiments, just as a sort of general thing. He said this to the class, and I still remember that, and I don't know how much of that particular comment influenced me, but this general idea that I think you sort of, in school, you basically only do theory somehow, like in classes, right? You're calculating things, and you have to go out of your way to actually get the experience of being in a lab and doing something more hands-on. And so a lot of people don't even know whether that's something they would enjoy or not, right? And I do remember very consciously deciding, okay, I want to make sure I do like an experimental project this summer and get a sense of like, is that something I like to do? Part of the reason that I felt that way is I actually really did love the more sort of abstract theoretical things I was doing. So I mentioned I did like a secondary concentration in math. Some of my favorite classes my freshman and sophomore years were things like, abstract algebra, those really proof-based classes where you get to, just get really deeply mentally into trying to, figure out some proof. I found that really satisfying. But I also somehow thought, can I imagine my whole job just being to think? And I couldn't quite imagine that. So I thought, I love math classes, but I don't think I want to be a mathematician. And I had this sense that in physics and in experimental physics, you would get a nice balance of being able to do some hands-on things, but also being able to sit down and calculate things, and that you could kind of have it all. And I do actually feel that that's been true for me. I mentioned what I like about my field is that the systems that we build there's a lot of complicated hardware that goes into it. But at the end of the day, what you strive for is having in the lab something that has a pretty clean theoretical description. It may be hard to calculate what will happen, but you can sort of write down the Hamiltonian, the equations that describe the system, and they map pretty well onto what you have in the lab because, like I said, every rubidium atom is like every other rubidium atom. You can maybe reduce it to the case where all that matters are two internal states that you think of as a spin. So there's this way of going from the hardware, which is fun in its own right to deal with, but to that sort of elegant description that you can write down on paper and calculate things about. And I like getting to have to be on both sides of that. So maybe I'll say that some fields of physics have a very strong divide between theory and experiment. And this field of atomic physics is one where you're more likely to have people who do a little bit of both. And I do occasionally have some idea that seems worth calculating, and my students and I will write a theory paper because we're not quite ready to do the experiment, but it seems like maybe somebody else would do it, or it's just worth writing down and working out, right? And so we do a little bit of theory on the side.
Thank you so much.
Great. Okay, so I don't see other hands raised right now, so I will go. So this was sort of a digression into how did I get where I am. And so, in particular, I would say I was sort of raised in this area of actually using atom-light interactions to generate useful entangled states. In some sense, though, much of what had been done in this field was sort of generating states that are conceptually simple. So I drew some picture here of the total magnetization of this system of spins and the fluctuations around the average being squeezed. And the fact that I can even draw a picture of a quantum state, in this case, this is some system of many thousands of atoms, that suggests that somehow I'm not yet exploring this full complexity that I described, where the description shouldn't even fit onto a supercomputer. So, one of the questions that I kind of started to wonder about more recently is, can one take this toolbox and actually apply it to some of these other directions of, quantum simulation? I realize some model that is conceptually simple, but it's hard to calculate what will happen. And so you need to build the experiment and see, and maybe that tells you something about material science or maybe even about quantum gravity. Or can we actually sort of perhaps take these tools and use them to solve some of these optimization problems? So with sort of those goals in mind, we decided to I will actually say I didn't precisely have those goals in mind when I built this setup. Sometimes ideas evolve, but I'll present it in that way. So we decided to build a setup where we have the ability to have these photon-mediated interactions between atoms, and also the ability to kind of take pictures of the atoms and see what's going on and watch kind of the dynamics of the quantum system, and have also a high level of control over the interactions, which I'll get to in a moment. But just to kind of first show kind of a picture of the sort of one of the experimental setups in my lab, I gave this cartoon picture earlier of putting atoms between mirrors. These are actually the mirrors that form this optical resonator. So it's literally like two mirrors 5 centimeters apart. This is all inside a vacuum chamber. There's a window here and a lens outside the window where we can look inside and take pictures of what's going on. Okay, and here are some of the students who had to build this up from scratch. And once you have that vacuum chamber set up, then the first thing you do is you want to get some laser-cooled atoms that are sort of atoms at low temperature that are a starting point for our experiment. So here's kind of a picture of a cloud of some millions of atoms collecting in what's known as a magneto-optical trap. And we're just detecting the fluorescence here on a camera. So that's sort of a standard workhorse of many modern atomic physics experiments, which is a starting point. That's the atoms are getting cooled and collected, and then we trap them, in our case, in an array of about 20 little clouds of atoms. So earlier I showed you pictures of single atoms. In the experiments I'll show you from my lab, we're working with little clouds of about thousands of atoms each. And that turns out to have some advantages for these photon-mediated interactions to enhance actually the strength of the interactions. So that's what we'll be working with in what I show you today. And to sort of tell you a bit more about the physics that's going on, I first need to sort of zoom in on what are these individual atoms. So in our case, the atoms are rubidium atoms, and it turns out I gave you some cartoon picture of interactions in the case where each atom has two internal states that I called spin up and spin down. In our system, actually, each atom will have three internal states that matter. So I'll call them -1, 0, and 1. And so in this system, the type of interaction that we can study, so again, I think of these as kind of spins oriented in opposite directions, but there's one state here with no average magnetization. And the type of physics we can study is, for example, if I start with two atoms in this 0 state and I send in light, I can have a process where a photon bounces off one atom and flips it to the -1 state and flips the other one to the +1 state. So I call this pair creation. You take a pair of 0 atoms and turn them into a +1, -1 atom. And in general, there's no reason why the one in the left or the one on the right should be in the +1 state. So you would expect this to be a mechanism for generating entangled states that look like, I have an equal superposition of being in -1, +1, or the opposite configuration. So that's what you would expect for two atoms. We do experiments, as I showed, with many atoms. And so the type of thing that we can do is, start with all atoms in the 0 state in this array of little clouds, and turn on some light that should allow them to interact and watch what happens. So, here's 30 repetitions of the same experiment, where after turning on the light for some period of time, we measure how many atoms are in the -1 state, the 0 state, and the +1 state. And we're doing this in kind of a site-resolved way. So like each little box here is showing kind of the number of atoms, let's say in the 0 state, in a given site of this array. Okay, and one thing you'll see is there are kind of large fluctuations. Sometimes you see a lot of atoms in the -1 state, sometimes there are fewer, but they're always kind of correlated between the -1 state and the +1 state. And this matches this idea of every time I generate a -1 atom, I have to also generate a +1 atom. So this idea of the pair creation. And you also kind of are seeing this idea of the correlations and the randomness that I said are a hallmark of entanglement. These measurements alone, I should say, don't prove entanglement, but they're consistent with this process of generating many of these entangled atom pairs. Okay, so that we were happy to see that we can generate these interactions that are mediated by photons, and you can also start to see something about the non-local character of the interactions in the sense that these correlations kind of extend across the entire cloud, right? There are these fluctuations, but if more atoms are in the -1 state, that's true kind of across the entire cloud. And that's because, in general, if we don't do anything special in this system, the light allows every atom to talk to any other. A photon emitted by one atom can be absorbed by any other. So I said we wanted to have some programmability of the connectivity of interactions in this system. So how do we do that? So sort of the next step we take in order to have some more control over the connectivity of the interactions is we apply a magnetic field gradient across our system. So the idea is, normally in the absence of the gradient, I could create a +1 atom here and a -1 atom anywhere else, but in the presence of the gradient, that pair creation process only conserves energy if the atoms are in the same place, basically because the splitting between +1 and -1 depends on the position in the cloud, right? So I want the energy cost of creating a +1 atom to balance out the energy lost by creating a -1 atom, and so the atoms need to actually be in the same place. And that means that if I now measure sort of correlations between how many +1 atoms are there on one site and how many -1 atoms are there in the other state and the other site, so like +1 atoms on site I versus -1 atoms in site J, we see that there are strong correlations. The color indicates the strength of correlation here on the diagonal, meaning sort of on a given site, this is indicating essentially that the interactions are localized to individual sites. But now we can play a trick to say I would like to turn on interactions at some distance that I choose. And the way that we do that is to send in two different frequencies of light. So the atoms can absorb a photon of one energy, and another atom can emit a photon of a different energy, and that can bridge the energy cost of creating a pair, +1, -1 pair, at some spatial separation. So now by sending in these two frequencies of light, we can generate, this shows up in some correlations off the diagonal. This is just saying we've turned on interactions at a particular distance that in this case is, I think, 10 sites. And if you vary the separation between those two frequencies, so sending in these two frequencies is equivalent to saying I send in a modulated intensity. So then there's a modulation in the intensity at the difference frequency. This is like if I tune my violin, I can sometimes hear a beating um, at a frequency that corresponds to the difference in the frequencies of the strings. Okay, so this intensity modulated light allows me to turn on interactions at a given distance where the distance is set by the modulation frequency. And this is just showing some correlations as a function of distance in each row. And vertically, I'm varying the modulation frequency, and I'm saying the distance at which I see correlations tracks the frequency. So this is just saying I can turn interactions on at a specified distance specified by the frequency at which I modulate my light. And you can really decide, are the interactions on at a distance of 8 sites or 9 sites or 10 sites? Andrew, yeah.
So with this model, or sorry, with this system, say you have, so you can turn on the interaction between one pair of electrons, or one pair of atoms, or atom clouds, whatever. And then, so you wanted to, you're still limited by the number of lasers. If you wanted to turn on multiple interactions, you're still limited by the number of lasers, right? Because you can't just change the frequency by like passing it through, I don't know, some filter or something on the way out or something, right?
Yeah, so I can emphasize these two frequencies of light, these are not generated by different lasers. That's really a single laser. And all I need to do is modulate the intensity with something called an acousto-optic modulator. It's just a device that allows me to kind of modulate the intensity of the light. And it's very easy to take an arbitrary waveform generator, sort of standard, piece of electronics that we have in every lab, and design the waveform in order to control, do I modulate at a single frequency, or do I perhaps modulate at multiple frequencies? And so that allows us actually, and that was actually the next point on the slide, more generally to control the graph of interactions by controlling the waveform with which I modulate the light. And that turns out to actually be an easy thing to do, is to control that waveform. So great question, yeah.
Okay, cool. Yeah, very cool. So you could, in principle, you could just have one laser at one frequency and just using like a sequence of AOMs, pass the beam through like spatially you could separate it and then use different AOMs and then address every interaction if you wanted to, with just however many AOMs you needed to do that.
Yeah, so in our case, we can use a single AOM. So again, the AOM, for those who don't know, is what modulates the intensity of the light, and have multiple frequencies to generate a more complex waveform that will turn on interactions at different distances.
Oh, okay, even better. Wow. Okay.
And then those distances, that then applies to the entire system. So like every site interacts with the site that is, let's say, 3 away or something. In principle, if you have multiple beams, then you could have even more complex control, but that's not something we're doing right now. Yeah.
Awesome, thank you.
Mm-hmm. Yeah, and so actually, so here's an example where we tuned things so that every site interacts with the site that's 3 away. So we turn on interactions at a distance of 3 sites. We measure the correlations. And then one of the cool things my students figured out is that there's a way to go from the measured correlations between the different sites to actually sort of reconstructing some effective geometrical picture of the graph of interactions we've generated. So they actually take these measured correlations and they say, is there some way to sort of take what we really have physically as in a one-dimensional array, but is there some way of sort of plotting the positions of the array sites in 3 dimensions in such a way that in this 3-dimensional geometry, correlations actually decay just as a function of distance? So this is kind of a way of, from the data, reconstructing a visualization of kind of the graph of interactions. And the bonds are colored according to the strength of correlations. And so in this particular example, we have interactions at a distance of every 3 sites. And this basically acts like 3 decoupled chains instead of a single chain, right? 0, 3, 6, those all interact. 1, 4, 7, those interact separately. And so this ends up acting like a system of 3 separate chains. Okay, so that's kind of a first step. But now you can do things like add another frequency that links these different chains. So in this, here's an example where we send in 2 different modulation frequencies. In this case, we designed it so we have nearest neighbor interactions. We actually have a trick for connecting the ends of the chain, so we have periodic boundary conditions. And then actually, we decided let's add a bond across the ring. And we measure some correlations, and then you can ask sort of what is the best representation of this graph of interactions if we just directly reconstruct it from the experimental data. Anyone have a guess, actually? What will pop out, like in the same way that we got these 3 chains here? Okay. Okay, so I'll give it away. So what pops out here is actually a Mobius strip. So that was kind of fun. So this sort of circle around the chain is the single edge of this Mobius strip. And the bonds across are the sort of transverse, the width of the Mobius strip. And we can even control, are the interactions, do the spins want to align or do they want to anti-align? So red means that they end up aligned, blue means that they end up anti-aligned, and it's just the phase of the modulation waveform that lets us control kind of the sign of the interaction. And you can kind of visualize this as now neighbors want to be as aligned as possible, but across the ring they want to anti-align, and so the spins are kind of winding around. Okay, and then you can program in different waveforms. And this is just kind of a gallery of a few different sort of graphs of interactions we made to kind of illustrate the versatility of the technique. So you can have this Mobius strip, or you can have a cylinder without a twist. You can have some kind of a ladder geometry. So now we're sort of have realized at least fairly versatile control over the graph of interactions, which is something I kind of set out to do from the beginning. I gave this motivation in terms of optimization, so I want to give kind of a flavor of sort of how this system can be used for that. It's actually not immediately obvious that the system should minimize its energy. I just sort of send in light and the spins will interact in some way, but what's the mechanism for it minimizing its energy? Well, it turns out that in our system, actually creating this +1, -1 pair costs a little bit of energy. The energy of a +1 and a -1 atom is a little bit more than the energy of 2 zero atoms. So it turns out every time we create a pair, we increase the internal state energy a little bit, and we have to lower the interaction energy to compensate. And so, for example, if you make something like this sort of ladder where they're kind of triangular plaquettes and the spins want to anti-align on them, they can't perfectly anti-align, but the best they can do is sort of organize themselves at 120-degree angles. This idea that they can't quite anti-align the way they would like to is called frustration. And the data that we measure is kind of consistent with the spins having that 120-degree ordering that is the lowest energy configuration on this particular interaction graph. And so one of the things we're really kind of curious about is, here we actually knew what should happen, but can you apply this to some more complex interaction graph where it's actually a hard problem to minimize the energy? And is there some way that these quantum dynamics of the pair creation can help to solve that problem? That's a direction we're really kind of excited to explore. So I kind of gave you a little bit of some examples of how these atom-light interactions are useful for engineering specific entangled states, and also perhaps useful for this direction of optimization. I would like to say a little bit about simulation, if I have the time. Do I have a few minutes to say a little bit about simulation?
Yeah, absolutely.
Okay, so maybe I'll wait till the end for remaining questions, because I know that we've been going for a while. So the sort of last direction that we're kind of exploring is, can you perhaps simulate some phenomena from other areas of physics? And one that I've become sort of interested in from talking to my theorist friends is, can we build toy models of quantum gravity in the lab? So what do I mean by that? So this whole idea that one might be able to explore something about quantum gravity comes from a really elegant theoretical idea that there are certain quantum systems, let's say like here I've kind of sketched some two-dimensional system of interacting spins, that have a mapping to some, where there's a mapping between some interacting quantum system in d dimensions and actually a classical system with gravity in one additional spatial dimension. So this idea is known as holographic duality. Roughly the picture is that in coming up with some description of the quantum system that captures the structure of quantum correlations and entanglement, one can go through a process of sort of coarse graining to try to sort of capture what are the sort of group these individual spins into larger blocks that in a way that preserves or that captures the structure of correlations in the system. And that process gives rise to sort of this effective dimension. And in certain cases, that effective dimension has some space-time curvature and gravity. So that's kind of this idea of holographic duality. And I found this idea intriguing because it kind of says there are maybe some cases where this complexity of entanglement actually can be distilled into some geometrical picture that perhaps gives some new intuition for how to think about the system or even how to calculate something that would otherwise be hard to calculate. So this is a nice idea on paper, but is it actually useful for describing any system that one can realize in the lab? And if it is, maybe this would shed light on this sort of fascinating theoretical concept that gravity could be something that emerges from quantum entanglement. Okay, so but to be able to even start to explore that in the lab, you need maybe some idea of a model that might exhibit this phenomenon of some holographic duality, or at least some sense of an emergent geometry that emerges from the structure of quantum correlations. And so I was fortunate to collaborate with Steve Gubser, a theorist, who actually formulated a particular version of this idea of holographic duality, where the idea is that you have a physical system of like n sites that I can think of as living on kind of the leaves of a tree. And the tree represents this extra dimension, this sort of holographic bulk geometry. And actually, so if I have n sites and it's on a binary tree, then the depth of the tree is only logarithmic in the number of sites. If I wrap it around to live on a ring, then it's something like, instead of the circumference being proportional to the diameter, it's exponentially larger than the diameter. And so in some sense, this actually looks like a space with negative curvature. It looks like a hyperbolic space. Okay, so the idea is the leaves of the tree represent the physical system, and the idea is that there should be some kind of, that the tree represents something, though, about the structure of correlations in that system. And there are people who have actually literally physically built quantum systems, like arrays of superconducting resonators that are organized, that have a tree-like graph of connections. But what we were curious about is, can we build a physical system where this tree isn't physically there, but it somehow captures something about the correlations in a quantum system that we build in the lab? Okay, so there's a toy model that we worked out that actually kind of captures this idea. And the idea is, imagine you have this array of sites, and each site talks to other not nearest neighbors, well, not only nearest neighbors, but any site that's a power of 2 distance away. And then you can look at variants of this, like if those interactions decrease with distance, the graph looks like this, and it's not that different from a nearest neighbor chain. But if the interactions increase with distance, so the largest power of 2 is the strongest interaction, then it looks kind of weird. This is my graph of interactions. And it turns out, if I now kind of reorder these sites, it'll start to look a little bit more structured, and the conjecture is that the structure of correlations that would arise from these interactions is well described by the tree graph. Okay, so is that actually true? I mean, we can just program in these interactions in our system by programming the spectrum of the laser field. And we measure some correlations between the different sites as a function of distance. There's some weird behavior where the correlations are, well, they're strong at distances that are powers of 2. It turns out if you now reorganize this same data according to the positions of the sites on that tree graph, so I'm just reordering the sites, then it starts to look more structured. I start to see blocks where the correlations are strong near the diagonal. And it turns out if you kind of plot the strength of correlation versus the correct measure of distance on the tree, they kind of smoothly decay in a way that says the tree is a good representation of the geometry of this system. And lastly, you can actually say, let's take the measured spin correlations and do some kind of coarse graining procedure like the one I showed conceptually before, where we say, let's like draw a bond between the spins that are most strongly correlated, and then treat those as a larger spin and draw another bond, and so forth. And actually, so directly from the experimental data, when we do that process, actually this tree graph comes out. And so this is kind of a toy model for this idea of some holographic bulk geometry, so this sort of additional dimension that emerges that captures something about the structure of quantum correlations in the physical system. Okay, and so we were happy to see that. One kind of other neat thing is that if you sort of try to smoothly tune between the case where interactions shrink and the case where interactions grow, one is kind of roughly a linear chain, one is a tree, and somewhere in between everything is strongly connected to everything else. We have the conjecture that this might be a good model for that phenomenon of fast scrambling that I mentioned earlier, which is a model for what happens to information that falls into a black hole. So that's something to explore in the future. At this point, I think I've definitely used up the time, so I'll just kind of conclude by saying I've shown you this physical system where we have an array of ensembles of cold atoms with a high degree of programmability of the graph of interactions. And we're really interested in applying this towards asking, can we use that perhaps to solve these optimization problems that map to particular interaction graphs? Can we go deeper into exploring toy models of quantum gravity? And can we also use this as a way of engineering specific structures of entanglement that might be useful for either enhanced precision measurements or computation? So with that, I'll just also just show a picture of my research group and stop at this point and take any more questions.
Yeah, so go ahead and raise your hands if anyone has any questions. And maybe to get us started, I have one quick question. So in John Doyle's lab, and as you know, Professor, as an alumna of the lab, we do a lot of things with molecules, and they have these interesting properties that people have thought about for quantum simulation, like a large dipole moment that can result in things like long range interactions, which can be useful. And I'm sure you've thought, or have you thought about the ways that using molecules in your system might result in different phenomena or different ways to construct these graphs? Or maybe, because I can imagine like a naive model in my mind of where you don't even need a laser, but you can just set up like a ring of atoms and then you already have like an all-to-all sort of graph right there. If you had quantum control over the spin states of the molecules, or maybe like of the molecules. Have you thought about how
Yeah, so this is a great question. Maybe I can say a couple of things. So one thing I've thought about more than about molecules is about Rydberg atoms, because that's also something we work with in my lab, but not in the system I showed today. And in some sense, there's a similarity in that both Rydberg atoms and molecules can have some long-range dipolar interaction. It's not this weird non-local interaction. It still decays with distance, but it can be long-ranged. I think so one direction that is potentially interesting in the sort of sphere of quantum simulation, or sort of kind of realizing new states of matter, for example, is asking what happens from the interplay of these dipolar interactions and the all-to-all interactions mediated by the light field. And there are some predictions about sort of having new topological states of matter that are potentially interesting for robust encoding of quantum information that would come about through this interplay of the short and long range interactions. So that's one direction. I think another direction that is potentially interesting is obviously the molecules are wonderful for precision measurements, like these precision measurements of EDM measurements, for example, right? And I think one question is kind of, if you want to enhance that type of precision measurement by entanglement, in the same way that I've worked on enhancing clocks by entanglement, what is the best way to do that? Is it leveraging the direct interactions between the molecules? Maybe, but it's sort of challenging to make long-range entanglement with interactions that decay with distance. And so there's sort of a question of, you could imagine that maybe one day you would even want molecules in some kind of a cavity that gives you also the all-to-all connectivity, right? So I don't know. I think there are lots of possible directions to combine these ideas. I don't know. Does that answer the question?
Yeah, absolutely. It's really interesting to think about.
Yeah.
Okay.
Luke.
Hi, yeah, thank you very much for the talk. I had a question. You mentioned Rydberg atoms, and I guess when you think about quantum simulation as a whole, how do you go about in your lab choosing the specific hyperfine levels that you want to encode this information in? Because there's, of course, a huge amount of variety in terms of the interactions and the different coupling strengths and over different distance ranges. So I guess how do you go about that challenge?
Yeah. So, I mean, the first step is kind of choosing an atom, and that gets kind of, once you've chosen that, though you're somewhat constrained, you buy all the lasers for that particular atom, and that sometimes has to do with what wavelengths are convenient and so forth. And then there's a question of, like, I think the question you asked, what states should I choose within the particular atom? And in the experiments I showed, we did something that I once thought I would never want to do, which is to work with states that are magnetic field sensitive. So often you might say, what I want to do is have my experiment be very immune to any environmental perturbations, and so I want to choose the states known as clock states, which are the ones which are to lowest order insensitive to the magnetic field. And so there are other experiments I've done where actually the clock states are the two states that you use to encode a spin. It turns out that for the experiments I showed today, you'll notice we actually kind of took advantage of the magnetic field sensitivity to have control over kind of the energy cost of creating these pairs, and to be able to use the spectrum of the laser field to engineer the graph of interactions. And it turns out that actually this mechanism is relatively robust even to fluctuations in the magnetic field, because an overall change in the field doesn't matter, only changes in the gradient matter. And so then the other question is, what do you want to do with the system? Maybe you actually want to build a magnetometer, and then you can take advantage of that magnetic field sensitivity. But yeah, so I don't know, hopefully that gives a little bit of a flavor. If you want to be magnetic field insensitive, it turns out in these alkali atoms, there's one very natural transition to use, that is this clock transition. And for us, we wanted the magnetic fields to help us get control, and so we chose these Zeeman states within the atom. Great, Bernie.
So I have a question. So I find it really interesting that you can study very fundamental physics things like quantum gravity with this atomic system. Also, like you mentioned, people are doing precision measurement on like EDM and fine structure constant. So how do you think these methods in the study of atomic system can be compared to the conventional method of studying fundamental physics, like high energy collider? Like how do you think these paradigms can compare with each other or complement each other?
Yeah, I mean, so I think, in high energy physics, the challenge is at some point it becomes some prohibitive to keep building higher and higher energy colliders, right? And so to the extent that it is possible to access similar information by doing very, very precise measurements of low energy systems in the lab, that's a very valuable complementary tool set. So I would say there's kind of maybe these different paradigms for accessing fundamental physics. Certainly the colliders are one that has been very valuable, but the ability to do sort of more and more precise measurements, for example, comparing atomic clocks of different species, can give you sensitivity to things like, is the fine structure constant actually constant, or is it varying in time, right? There's lots you can do by just pushing the precision of measurements that we can do. And so, in one direction that is really kind of still a challenge, but I think we're moving in the direction of being able to even use entanglement to actually take those best measurements and make them even better, and that opens exciting possibilities. Where, for example, atomic clocks are getting to be so good that you can almost think about using them as gravitational wave detectors. They're not quite good enough yet, but maybe you can get that extra push by entangling them in sensitivity and start to use these clocks as sensors. Then there's the really, I would say, totally complementary direction of simulation that I talked about, which is, can we sort of connect experiments to some of these, what hitherto were like very abstract ideas from people thinking about what is the nature of quantum gravity, right? And so, ideally you would love to do precision measurements that probe sort of like Planck mass objects in the quantum regime, and that's an outstanding challenge. That would be great. But meanwhile, we can take this idea of, is there at least some model system in the lab where there's a sense in which some space-time curvature and gravity could emerge from entanglement? Does that tell us about gravity in our universe? Then we need to go back and talk to the theorists, and I'm not sure. But if nothing else, maybe it allows us to take some of these ideas from people who've been thinking deeply about quantum gravity and actually apply them to get some new way of modeling the many-body systems that we do build in the lab. So, yeah. Minchol.
Thank you so much for the talk, by the way. And I have a question about the general quantum simulation. So when we want to make a quantum simulator, what is the standards or what is the parameter that we usually consider whether it successfully models the system that we want to describe, like quantum gravity or condensed matter systems?
Yeah. I mean, I think there are different standards you can use. So I would say in this idea of kind of quantum gravity, I think this is at a very early stage where even just we're at the stage of, I would say, almost communicating between theory and experiment is something that didn't happen at all until a few years ago. And so, and there's a huge language barrier, and even sort of trying to sort of, for me as an experimentalist, trying to understand what are the concepts that from the theory side that could be probed in the lab, you know, just thinking about, yeah, just even sort of building an experiment that gets at some of these concepts, to me is already sort of a small step. And then you need to build on it, and now we really need to go back and ask, you know, what's the next thing one should actually measure to, you know, learn more about quantum gravity, or sort of what are the predictions that might come from the side of thinking about gravity for what we should measure in the quantum system that might not be obvious from the perspective of thinking about quantum mechanics. So I think there the success is even just bridging two disciplines that were totally separate before. But then more generally, there's a goal of really sort of answering in the quantum simulator a question that can't be answered in a classical computer. So some of my favorite examples that by now are about 10 years old were experiments that were done with ultra-cold gases of ultra-cold fermionic atoms, where you can ask very simple questions like, we know for an ideal gas, we know that PV equals nRT. But if you have a strongly interacting gas of fermions, what is the analogous equation? And that's hard to calculate. There are ways of trying to calculate it, but you know, different theoretical models were disagreeing. And then precision measurements were done in these ultra-cold gases to sort of nail down that equation of state and sort of say this theoretical model is working better than that one, right? And when you can really get to this point where you can use the experiment to start to discern which of the theoretical methods are working best and improve the theoretical methods, I would say that that's really definitely a success for quantum simulation. And then, of course, once you get into the regime where the theory just, you know, breaks down, then it becomes even harder to ask the question, how do you verify that the simulator is doing the right thing, right? And that's something that people are starting to have to grapple with now with this sort of scaling up of quantum computers. So, yeah. But I think it's always a moving target, right? What constitutes success, and it's good if the target kind of moves. So I would say in quantum gravity, the target is still like, it's very low. It's even just doing any experiment that connects to these ideas, and then we're going to push it to, you know, can we actually learn something new? Can the gravity help to predict something about the quantum system that we didn't know should happen, right? So yeah, we'll keep pushing that target ahead. Yeah. Helena.
Hey, thank you for your talk. It was definitely very interesting. I have a question. So like, I saw like your earlier part, like you introduced like your work on kind of like these, basically like you were able to like find all these like tree structures and stuff like with your atomic arrays and stuff. I was just wondering because I was thinking that like, you know, tree structure is kind of like a fundamental thing, like not like I guess in like computer science like at all. So like not even like the quantum part, but just like even classical algorithms and stuff is like one of the most fundamental like data structures and stuff. So have you thought about just like how like your new protocols and stuff can be incorporated into like, I don't know, like classical routines? I feel like really helpful if like, you know, like this protocol is developed into a very fast module, and you like incorporate it into like much larger like classical algorithm routines, and that can kind of like make like it just like kind of changes everything. Like, have you guys thought about how to incorporate like the quantum part and the classical part?
I haven't thought specifically about the question that you're asking, but I think maybe I'll say that more generally, there's sort of a direction of what are known as quantum-inspired classical algorithms, where one, you know, starts with an idea for sort of how would you design the quantum algorithm to do something, and maybe you can't actually implement that quantum algorithm yet because we don't have a full error-corrected quantum computer, but it gives some insight into how you could actually design a better classical algorithm, because, you know, in quantum mechanics you don't just have bits that are 1 or 0, you have phases, right? And that might give some new way of thinking about the problem. And so there are some cases where just thinking about the quantum system has inspired new classical algorithms. In our system, I haven't thought about applications of the tree graph that we can build in the lab to classical algorithms, but maybe I should. So, yeah.
Okay. If there are no other questions, then I wanted to thank you again, Professor Schleier-Smith, for an excellent conversation today. It was really a pleasure to hear about your career, how you got into physics and your current research interests. Absolutely astounding and flexible experimental toolkit. It's extremely exciting to think about the future of this work. And for the audience, I hope to see you all in 2 weeks for our final quantum summer talk at Chilloquium. Once more, thank you so much, Professor Schleier-Smith.
Thanks for the invitation and have a good evening. Bye.